Continuing physical chemistry, chapter 18. Now we're in section 11. We're going to talk about operators. Now here are some examples. Like let's say you have the square root of 2. Then the square root here is an operator because the square root does something to 2, which gives us 1.41, etc. Or let's say you have the logarithm of 2. Then the logarithm is an operator because logarithm does something to 2 to give us, 0.30, etc., etc. Or d by dx of x. Then we say the derivative with respect to x, that's an operator because d by dx does something to x to give us 1. Or let's say we have x squared, then this, squared is an operator. Likewise, let's say we have psi star, then that star is an operator because it does something to psi to give us the complex conjugate of psi. So if A is an operator, we symbolize it by putting a circumflex over the top. So let's say we have two operators here. So A circumflex plus B circumflex times f of x is defined as, remember 3-line equal sign means defined as, or always equal to, A circumflex of f of x plus B circumflex of f of x. Likewise, let's say we have a circumflex squared of f of x, then we define that as taking a circumflex of f of x and then taking that a circumflex of the result. Likewise, order of operation, let's say we have a circumflex of b circumflex of f of x, then we're defining that as taking b circumflex of f of x first and then taking a circumflex of that. Now, let's say that b circumflex of f of x equals c circumflex of f of x, then that means that b circumflex is equal to c circumflex. In other words, the b and c would be the same operator. So, here's the question. Let's say we have a circumflex of b circumflex of f of x equal to b circumflex of a circumflex of f of x. Are these two equal? They can be. It depends on what A and B are. Also, so order does matter, but by coincidence it's possible they'll be the same. So A circumflex and B circumflex, they may or may not commute. Commuting means switching the order. So each physical property has its own operator. So an observable, it's a physical property that we can measure. For example, here's a table of observables and operators. So for position, we have x, y, and z in rectangular coordinates, obviously. Then we have an x hat operator, a y hat operator, and a z hat operator. Likewise, momentum, we have an x, y, and z. So for x, we have the rho hat of x, and that's equal to h bar over I. Remember, I is the imaginary number, square root of -1, times the partial derivative with respect to x. And this is postulated. And remember, I squared is equal to -1. Likewise, for rho of y, we have this rho of y operator, and that's equal to h bar over I times the partial derivative with respect to y. And then, of course, same thing. For momentum of z, we have the momentum of z operator is equal to h bar over I times the partial derivative with respect to z. So for energy, E, it's equal to the Hamiltonian operator, h circumflex. Now, then there's time. There is no operator because it's not observable. Instead, in quantum mechanics, time is considered a parameter. And like I said already, h hat, that's the Hamiltonian operator. This is the Hamiltonian operator. It's minus h bar squared over 2m times this whole quantity, the partial derivative with respect to, or second derivative with respect to x, plus the second derivative with respect to y, plus the second derivative with respect to z, plus the potential energy, which is a function of xyz position, but also time. And that's this is multiplication. So V is potential energy, T is time. So remember, we abbreviate IFF means if and only if. It's the same symbol as going left and right. So if something is true one way and the other, we say if and only if. So let's talk about linear operators. B hat is a linear operator if and only if it has the following properties. 1, B hat of C of F is equal to C B hat of F, where C is any constant. And 2, B hat of F plus G is equal to B hat of F plus B hat of G. Now the square root operator is not linear, because the square root of x plus y is not equal to the square root of x plus the square root of y. Now, taking something squared, or the first derivative, the second derivative, those are all linear operators. All operators in quantum mechanics are linear. Now this del squared, that's called the Laplacian operator. Obviously it's pronounced del squared. Del squared is defined as the second derivative with respect to x, that's partial derivative obviously, plus the second derivative with respect to y, plus the second derivative with respect to z. So the Hamiltonian can be written as minus h bar squared over 2m times del squared plus v, where v is the potential energy. Now we're going to talk about the time-dependent Schrodinger's equation. So we have the Hamiltonian of psi. Notice this is a capital psi. And that's equal to minus h bar over I times the derivative of psi with respect to time. So that's the time. And then the time-independent Schrodinger's equation was the Hamiltonian of lowercase psi is equal to energy times the lowercase psi. So the Hamiltonian, that includes the potential energy, V, if there is any. Now the Hamiltonian times the psi of J is equal to the energy J times the psi of J. So J is whatever state that the system is in, particle is in. So psi of J is the allowed stationary wave function. Psi of J is a allowed set of energy levels. So if an operator on a wave function gives the wave function back times a constant, we say the function is an eigenfunction. So psi of J is an eigenfunction of the Hamiltonian operator. E of J is the eigenvalue. Hamiltonian is the energy operator. So we have the energy operator times the wave function is equal to energy times the wave function. So here we have the operator, and here we have the observable. Now let's say that f of x is equal to e to the 2x, and the operator is the derivative with respect to x. Then we have the derivative with respect to x of e to the 2x is equal to 2 times e to the 2x. So in this example, 2 is the eigenvalue. So that means that f of x is an eigenfunction of the first derivative with respect to x. Now let's talk about average values or expectation values. Okay, let m be some physical property. The average value of m in quantum mechanics is given by this equation. Notice m in brackets like that, that means average value of m. So we have this integral. It's understood that it's triple integral because it's we're in 3D space here. So we have the complex conjugate, psi star, and then m hat, so that's our physical property we're looking at. Well, the operator for the physical property we want. And then the psi, these are lowercase obviously, and then d tau. Remember, tau means over all space. So that's why it's a triple integral. So this is postulated, not derived. So if psi is real, then you can just use psi instead of psi star. Because if it's real, then obviously it's equal to its own complex conjugate. So like here's rho hat of x is equal to h bar over I times the derivative with respect to x. So we have the expectation value, or the average value for the momentum in x, is equal to h bar times the integral from minus infinity to infinity of the integral from minus infinity to infinity of the integral from minus infinity to infinity of psi star times the partial derivative with respect to x of psi with respect to x, y, z. Now let's talk about non-interacting particles. which is not realistic, but you know, we got to start with a model somewhere. So we get psi is equal to f of 1 of x1, y1, z1 times function 2 of x2, y2, z2, etc., all the way to function n of x position of particle n, y position of particle n, z position of particle n. So these are different functions, f1, f2, f3, etc. Now the averages or the energies are scalars, right? The total energy would be the energy of particle 1 plus the energy of particle 2 plus the energy of particle 3, etc., all the way up to the energy of particle n. So the Hamiltonian operator here, h hat of 1 of times f1 is equal to energy 1 times function 1. So remember, f1 is the eigenfunction of the Hamiltonian, and e1 is the eigenvalue. Oops, I'm getting crooked here. And then likewise, got the Hamiltonian of particle 2 times the function particle 2 is equal to the energy of particle 2 times the function of particle 2, and so on for the Hamiltonian of particle 3 times the function of particle 3 is equal to energy of particle 3 times the function of particle 3. So what you have is an individual Schrodinger equation for each separate particle. So we have psi squared, absolute value obviously, is equal to f1 squared times f2 squared times fn squared, because they're independent probabilities since they're non-interacting. So the probability of finding all particles in the same spot at the same time. So we're doing this, we're going to be talking about rounder shapes, so it's actually going to make more sense to use polar coordinates instead, because an atom is so symmetric. That's all for section 11.